Let's talk maps. Texture maps. Specifically, let's talk about the texture maps used in a PBR workflow, which is what most modern game engines, 3D modeling, texturing, and rendering software uses. PBR stands for Physically Based Rendering. The goal of PBR is to try to accurately simulate how light materials look in real life. Primarily, I'm going to talk about the most common maps that you'll see used in game engines, and try to give a detailed breakdown on each of these texture maps, how they work, and what they do. To demonstrate this, I'm going to be showing examples in Blender and with Affinity Photo. Although this information is the same whether you use Maya and Photoshop or any other combination. I'm also going to be using this wooden table texture that I got from PolyHaven to demonstrate. We're going to start with arguably the most visually interesting map, the color map. Now, to be accurate, in a PBR workflow, the color map is actually called the Albedo map. Another term that you might hear used for it is the Diffuse map. Now, while Albedo and Diffuse are pretty much used interchangeably at this point, they are different. A diffuse map is an older term that was used before the PBR workflow. Essentially, a diffuse map would have some lighting information baked into the image itself, and the object's metallic data baked in as well, whereas an albedo map is just purely the color with no lighting. Although again, at this point those terms are usually talking about the same thing, which is an albedo map. These maps are pretty self-explanatory. They are just the color of the object itself, and use all three color channels to display that color. Now, the next map I want to talk about is this AO map, or Ambient Occlusion map. As you can see, an Ambient Occlusion map is in black and white, and that's because it is a single channel image. You see, textures and how they are used by shaders is pretty clever, and they can be used to store non-color data about an object. In this case, it's used to store the natural shadows of an object under ambient lighting. In this case, darker pixels represent natural shadows, and a fully white pixel indicates no natural shadow. For this example, you can see that it darkens the cracks and crevices between the wooden boards, as well as slightly darkening the wood grain. Now, depending on your game engine, there might be a specific slot to place in your AO map, but you can also manually add one in by multiplying your albedo map by your AO map. You could also choose to bake your AO map into your albedo map, which would officially make it a diffuse map, minus metallic data. One last note on ambient occlusion maps though. Depending on your needs, you may not want to use one in your game. If the object is going to be lit by a static light and doesn't move any, then go ahead and bake that lighting in with an AO map. But if you have a more dynamic object with global illumination, where a light could be shined directly on at any angle, then you might want to forego the AO map and just let the game's rendering calculate any of these shadows itself. Of course, you can always just play around with it and see what looks best for your individual project. Hopefully you're keeping up with all this and not having too rough of a time. So let's talk about roughness maps. As you can see, these are another single channel black and white texture map. Roughness can be thought of as how shiny an object is. More specifically, it's used to determine how light scatters along an object's surface. A roughness value of 0 or a black pixel means that light reflects back in a mirror-like way, whereas a roughness value of 1 or a white pixel means the surface is completely matte, with every shade of gray in between making up the values between 0 and 1. We can actually see this in action if I manually adjust the roughness values in Blender here. You can see as we approach 0 that light becomes more concentrated, as it reflects directly back into our view. As we go towards 1, you can see that light starts to spread out evenly across the surface, until it becomes fully scattered and appears matte. Now, the reason it's called a roughness map is because of how light reflection works in real life. Every object around you technically reflects light. That's how we see. But what makes an object appear shiny versus appearing matte has to do with the micro details of that object. Imagine how rough and bumpy concrete looks, and compare that to a glossy finish on a piece of pottery. If you looked at a matte object under a microscope, you'd see the object more closely resembles the roughness of concrete on a micro scale, whereas a shiny object is more smooth, just like a piece of glossy pottery. That's probably an oversimplification, but that is why it's known as a roughness map. The next map goes out to all the metalheads out there, and that is the metallic map. Metallic map is yet another single channel black and white texture map, only this time it holds the data for how metallic an object is on a per pixel basis. In this case, the texture map for this wooden table is entirely black, because a black pixel means the object is not metallic and a white pixel would mean the object is metallic in that spot. Since this is an entirely wooden object, there are no visible nails or anything like that. It is represented with an entirely black value. But because of that, there actually wasn't a metallic map that came with this wooden table material, because it would be a waste of storage space when you could instead just set the metallic value in your software to have a flat value of 0. But what really is a metallic map? It's obviously used for metals, but why does that matter? Well, once again, the PBR workflow tries to recreate how surfaces respond to light in real life and how metals in real life reflect light. Metals reflect their surroundings clearly, and in fact you can see this in action if you move the normal map, decrease the roughness, and increase the metallic value to 1. Despite the albedo map still being attached, the surface is reflecting the environment around it, just with a slight coloring from the albedo map. You can compare this to a shiny non-metallic surface, and the difference is pretty clear. Now, there are a lot of other single-channel black and white texture maps out there, but AO, Roughness, and Metallic are probably the most common ones you'll come across. Outside of those, there are emissive maps, which indicate what parts on a pixel level an object should emit light, with black being no emission and white being it fully emits light. There are opacity maps that determine translucency of an object, although usually those can be baked into the alpha channel of your albedo map. Which brings me to this next texture, the ARM texture. This map is what is known as a packed texture map. Remember how I mentioned all of those other maps are single channel maps? Well, a packed texture map takes advantage of that and saves multiple texture maps into the color channels of an RGB image. In fact, it can even save an additional map inside the alpha channel as well. In this case, because this is an ARM map, if we look at the individual color channels, we can see that the red channel has the AO map baked into it, and the green channel has the roughness map baked into it. And the blue channel is entirely black, which would be the metallic map. Hence the name ARM, Ambient Roughness Metallic. But why do this? Well, because it saves space and is a more memory efficient way to get this material information about your object. Imagine if you had 1,000 different objects in your game, each of those individual texture maps. That's the difference between 3,000 additional textures or just 1,000 additional textures. There's a couple more things I want to mention though about packed texture maps. Firstly, that is the packing order and the naming conventions of those packed maps. While this particular map uses ARM, it's not unusual to see ORM, RMA, RMO, or even MRO. The A and O both stand for Ambient Occlusion, and R and M are still Roughness and Metallic. The naming convention tells you which color channel contains which map, so always pay attention to that. Another thing is packed maps aren't limited to just AO, Roughness, and Metallic. Any single channel texture map can be placed into one of these channels. You could have an MRE map, a Metallic, Roughness, and Emissive map. Also, depending on the engine you're using, you might need to tell the engine that this texture map is not being used for color, and is purely being used for data, otherwise you might get some strange results. It's been a lot of talk now about packed maps, so let's finally return to something normal. Normal maps give per pixel normal information about a surface to your object. This allows it to fake bumps and fine physical details that your actual object doesn't have. Allow a single quad the illusion of detail that could otherwise require millions of vertices to actually model out. In fact, that is one of the main uses of normal maps, is to take the surface details of a very high poly model and bake those down to a normal map for a lower poly model. If you're watching this, then you probably already know what a normal is in 3D, but if not, I'll give a quick recap. A normal can be thought of as the direction a face is directed toward. Your vertices also have normals, but for this demonstration, I'm going to be using the face normals. So as you can see on this plane, each of the normals for a face are pointed straight up. If we instead look at this cube, you can see the normals change to match the direction of each face. By altering these normals, we can pretty drastically change the appearance of an object. Most obviously, these is the difference between smooth shading and flat shading. We can also manually adjust these normals to even make this plane appear as if it has a slight round bump in it. There are some other cool shading techniques you can use custom normals for, such as some stylized looks, which I will link down below. One last thing on face normals is the direction of the normal tells a 3D renderer which side of your polygon to render out. It will then use backface culling to skip rendering the backside of your polygon. This helps increase performance since it would be a waste for most 3D models to render both the front and back face, although there are usually options that you can enable on a per material basis to tell the engine to render both sides. Now that was a lot of information, but you can probably then guess what a normal map does. It doesn't replace the normals of your model, but it gives the shader access to per pixel normals by using the RGB color channels as the X, Y, and Z direction of each of those normals. What this tells your render engine is the direction light should reflect off of the surface of your object, which is what allows you to give off the illusion of greater detail on the surface of an object, telling it where highlights and shadows should appear. Speaking of that, you might remember how we talked about the roughness map being how much light is reflected off of your object. Well, for a normal map to work, you can't have a roughness value of 1, because that means the light is fully scattered across your object, and so no reflected light is there to be given the directional information from your normal map. Something fairly distinctive that you might notice about normal maps is the bluish purplish coloration they have. That is because the Z value of your normal map is stored inside the blue color channel, which if we're looking at the face normals of our plane here, the Z value is this up and down value, whereas the X and Y or red and green channels hold the data for left and right and up and down respectively along this plane. So because these normals are still primarily sending light back out away from the object, the Z value is always going to be a bit higher than your X and Y values, which gives normal maps a stronger blue coloration. The actual default normal map color on a 256 RGB color code is a red and green value of 128 and a blue value of 255. In Blender, these values are normalized, which means they are shown between a value of 0 and 1. If you take a flat image of that color and apply it as a normal map, it will look the exact same as if it didn't even have a normal map. Another thing I want to show here is the difference between these two normal maps. This one is made to work with OpenGL or Vulkan, and this one is designed to work with DirectX. Different game engines and software use these graphic APIs. The main difference is which Y direction is used for up and down. OpenGL and Vulkan use positive Y for Y up, and DirectX uses positive Y for Y down. The only difference between the two though is that the green color channel is inverted, which if we manually invert one of them, we can see the textures then look exactly the same. Most game engines even have a toggle to invert the green color channel within your engine, so if something looks off, try to look for that. But quickly recap here, with normal maps the RGB color channels are used to store the X, Y, and Z vector data for the direction light reflects off of your object. Because objects reflect light off and away from the surface, your blue channel holding your Z directional value, which is the direction of the face normal of your polygons, will always be stronger and have a 256 RGB value above 128, likely being above the 200 range. At least the vast majority of normal maps you'll see and use will have that, although there can be some rare exceptions. The very last thing I want to mention here is you can technically use normal maps in texture packing. With the texture packing I previously mentioned, you will usually be able to have just 3 texture maps for most of your PBR materials. However, in some cases that number can be brought down even lower to 2 texture maps by making full use of every color channel of your maps, including the alpha channel. I'm not going to go into more detail on this, but if you're interested, I'll link a fantastic video by Cloward on this subject down below. As a heads up, it involves the Pythagorean theorem. Anyway, I hope this video was helpful, and if it was, please consider leaving a like, subscribing, and letting me know in the comments what game development topic you'd like me to cover next.